All right. So you're doing a definition right now. This process XFT is said to be weakly stationary. If its mean function is time invariant and the correlation function or covariance function depends only on the time lag. That is this function. And let's see what other stories I'd like to tell you about it. Okay. So the definition comes naturally from our example, right? So now it's a very important property. What I did here, I wrote the representation of the process in the time domain. Some of you, of course, taking courses in dynamics, and you remember there, you can do analysis in the time domain or the frequency domain. But we try to do the same thing here. That is, we try to figure out how we can represent this process in the frequency domain. In other words, any continuous function, single Fourier, deterministic world, right? Any function can be represented by a sum of harmonics. We just need to figure out what should be the weights or the coefficients of these harmonics. So we try to do something similar here. In fact, even here you have this idea. These are the harmonics and these are the weights. Of course, I can, if I pull something out, I can immediately look how much energy it's on this each harmonic. But we want to do a little bit more. So this is an important result, which is based on Bochner's theorem, which I'm going just to state it. If the covariance or the correlation function is continuous, that is C, the correlation function, is continuous, then this is a statement of this theorem. And the proof is not very difficult, but it takes a few blackboards, so there's no reason really to get into it. I think you agree with me. So if that's true, then there exists an increasing function let's call it S, which is defined on the real line with value in the real line, which is also bounded. These are some details which I'm not going to use, but just for completing some writing here. With the following property, that the correlation function, and I'm changing notation here just to simplify our life, tau has this meaning here, that is time lag, can be expressed in this form, integral over the real line. That is from minus infinity to plus infinity. I omega tau ds, let's put nu rather than put nu there, ds of nu. So S is that magic function whose existence is guaranteed by Bochner theorem. Or shall I write it high? You cannot. Okay, I'm going to rewrite this formula. So I'm going to continue here, but let me rewrite it here. So what's written there is the following. Yeah, it's the same formula. Don't write it twice. It's the same formula. Yes?
So is tau the time interval?
Hmm?
Is tau as the argument?
Yeah, this is what I said. Tau is a time lag.
Okay.
So there's no reason to continue writing t minus s because they are in the weak stationary setting. So all it matters is an interval.
All right.
And this particular function has a name called spectral distribution. But what we are particularly interested in application in another, so here I'm careful with the notation. This is uppercase, this is lowercase. So I'm trying my best on the board. I hope you can see the difference, which is defined this way. That is a derivative. Okay? And with this setting, the formula becomes the following. So let's look one more time at what we have written so far. I think I said twice what I mean by weakly stationary process. So now we want to obtain an alternative representation of this process to understand it better with the frequency content. And we based on this result of a theorem which guarantees the existence of such a function S, which is increasing and bounded. Now, because this S is increasing, its derivative is positive, right? So this is always positive, right? And what we have here in this representation, we simply note that these two functions are Fourier pairs. One is a Fourier transform with the other. This particular function is called spectral density. And let's look at this formula and that formula there to see what the meaning is. In our example here, we found out that the correlation function, which depends just on the lag, right? The lag there is denoted by tau. That's the time lag. Is what? A summation of some numbers associated with harmonics. That this frequency nu k is associated with this ordinate. So you can think in this way. This is the energy associated with this harmonic. Well, this representation is just a discrete version of this integral. Let's think for a moment. What is this? Well, this is an harmonic. Of course, I can write that equation sum is sine and cosine. Again, think what you learn in Fourier series. You can write it with cosine and sine, or you can write in terms of exponential. So these are harmonics of frequency nu, and that's the energy, S nu d nu, associated with that particular energy, with that particular frequency. Let me ask you a different question. Forget of everything I said so far. Look at this integral. I give you S of nu, and I ask you, calculate this integral numerically. What you are going to do? I mean, not by formula. I'm not writing formula. Numerically, what you are going to do? What you have to do to calculate something numerically? First step, discretize. So when you discretize, what's going to look like? A sum with E at some frequencies, and whatever is under the integral in that particular interval S nu d nu. That it's exactly this form. I can write cosine, right? You know the relation between the exponential? Cosine of x plus minus I sine of x, right? This is a formula, identity. So you can't go from one to another, it's the same thing. And I'm sure when you did dynamics in the frequency domain, most likely you end up with this exponential. All right. So this is what we learned so far. Correlation function, which is directly the analog of two-dimensional vectors, right? There's no difference conceptually. But we end the twist here. We have this Fourier representation of the correlation function, and we constructed the spectral density. They are pairs. What I want to show now, a very important property, is that both C and S, that is correlation function and spectral density, are even functions. That is, you calculate the argument and minus argument, you get the same thing. Okay? So let's show this somewhere. But before I do this, one more thing in terms of intuition. So let's say if we scale this correlation function to be one at tau equal to 0. And I tell you the following. At tau equal to, say, 3, C of 3, it's equal to 0.9. The other case, C of 3, it's equal to 0.1. What you are going to tell me about these two processes? So let me be more specific. I take two arbitrary times, t, and the other one t plus 3, right? So the time lag is 3. And I give you this information. And I scale it to be 1 just to get the correlation coefficient, right? I tell you, case 1, this correlation is 0.9, and the other is 0.1. So I tell you that x of t is 20. And I ask you to predict what is x of t plus 3. In which case you think you are going to have a better prediction, case 1 or case 2? Case 1, very good. Why? Well, if I make it equal to 1, what is going to be? Exactly. If I make it here equal to 0, what's going to be? I have no idea. Okay? So this is what correlation tells you. Something about the memory of the process. That if I tell you the value of the process at this time, if I ask you at the next time with that process, if it has long memory, you have a very good prediction. If it has a very short memory, it has a very bad prediction. And incidentally, something which is done extensively in the literature is so-called white noise, which is a total misconception in terms of the use. And it's just a parenthesis, not under this title. Just make a parenthesis, since it just came to my mind. White noise, we say that something is white noise. If C of tau, I said it's proportional because I don't want to put a number. Is delta tau, you know what delta tau is? It's similar to Kronecker symbol. It's a constant. It's 1, say, if tau is equal to 0, and is 0 otherwise. That's the standard definition of white noise, and is used extensively in all but one books on random vibration. And it turns out that all the formulas obtained are correct, but all the derivation are wrong. And the reason is that the white noise you'll figure out right away. I ask you a question. If this is a delta function, what is going to be S? Again, it's nothing to do with probability. It's Fourier transform. S is a constant. Okay? And we are going to see right away, because S is a constant, its variance is infinity. Therefore, variance doesn't exist. All the other things are out of the window. You cannot go that way. The way it's done correctly is through so-called Itoc calculus, and this has been done. Okay? So now let's back to, after this close parenthesis, please. Now let's get back to what we were trying to accomplish here. Okay? It just occurred to me, and I couldn't help but tell you about it. Okay, we want to show that these are symmetric functions. By definition, right? Simply the definition. Future time, current time. Multiplies. Now, do you think I can write this? Is this true? And if yes, why? I mean, you are not going to get off the hook that easily. It's weakly stationary, right? All it matters, whether I'm looking at these two times or I'm looking to these two times, it doesn't matter as long as the spacing between them is the same. These are real numbers. The product of real number is commutative, right? So by the definition, it's an even function. Okay? Same you can show for spectral density. So I'm not going to show it here. If it's not clear, let's talk it later in the afternoon. This I have up to, I have up to 3 o'clock this session. Yeah, okay. Just to gauge me. All right. Okay. So now let's think a little bit how we are going to generate samples of such processes. So I'm going to give you some example of typical spectral density correlation function. And then the whole trick. Now, there are many ways of generating sample. I'm going to focus just on one. So the whole trick is to bring whatever process we have to this form by discretization. Once we go there, we know what to do. Okay? And we are going to do all these tricks for Gaussian processes, but if we've seen for vector processes, if I know how to do Gaussian, I know how to do translations. So in this way, we are going to be able to generate sample of any Gaussian processes and sample of this class of non-Gaussian processes called translations. So that's the sequence. Before I write one more question, if you look at this formula, can you see that the variance of a process is the area under the spectrum? What's the variance? Is a correlation for what tau? Covariance function for what tau? What's the definition? Let's look at the definition. Mean is 0, right, in our setting. If I set tau equal to 0, what do I have? The expectation of x squared, right? Since the mean is 0, is this a variance? So let's go to that formula. If tau is equal to 0, that is C of 0, it's equal to the integral this at 0 is 1 area under the spectrum. It's that simple. Don't try to complicate things. I mean, think of all this fancy and arbitrary, very abstract mathematics, where it's coming from. Engineer experiments. I mean, all the moments, all these mean and variance and the super moments, where do you think they come from? Didn't you learn in your strengths of material or whatever, center of mass? That's the mean under Lebesgue measure. What about the moment of inertia? That's the variance under Lebesgue measure. That's all there is. They come from there. And they are global properties. Some functions or representation, in that case with the geometry of the cross-section. They all come from there. And then, of course, you end up to very fancy things. The big jump in mathematics was from discrete to continuous, where you immediately have to use different tools because you cannot count anymore. Because the number of elements in the interval 0, 1 is not countable. It's an uncountable infinity. So this makes a huge jump and leads to significant abstractions. Okay. One more thing. Engineers really don't like that spectral density. Because what's that, a negative frequency, they say. And, it doesn't have much intuition. And they use another concept, so-called one-sided spectral density. Most of the time they don't call it one-sided, just, so let me give it to you, one-sided spectral density. Let me write it. That is, you take the positive part as the original defined spectral density and double it, so that's the one-sided spectral density. This is used almost exclusively in applications. So this is important to know about it. All right. So let me give you some examples. Yeah, oh yeah. Yes, thank you. So, as I mentioned, I think everything is to go. Yeah. Now I'm careful. Because you are so enthusiastic. So I'm going to write a few examples of spectral density and correlation function, they are Fourier pairs. And then we'll take one of them and see how we can generate samples. And as I mentioned, the idea is to get back to that form. And you are going to see it's an extremely simple exercise. But when you do numbers, real applications, one has to be careful. Because anytime you discretize, you bring an error in. And that error, depending on its nature, can be very, very bad. And I'm going to tell you something about very bad errors made in published papers in reputable journals, particularly when they apply to very long samples, which are necessary in fatigue studies, where you have input or stress field which fluctuates for a long, long time. And to give you the punchline of the story, what's happening, you produce samples which are periodic. So basically, you run the sample, run, but you don't bring anything new to the table because it's the same function over and over and over. And that can be a problem. And there are all kinds of tricks which you can compensate for us, for that. So these are the, thank you very much, I really appreciate it. So we are still with weakly stationary processes. And these are examples. And I'm going to write here the correlation function and the one-sided spectral density. in all cases, I'm going to assume that mean is equal to 0. There's no restriction when I say the mean is equal to 0. If it's not 0, I produce what I want to produce, and I add the sample. There's no reason to bother with it. There's no restriction, absolutely. Even if it's not stationary, I can do the same thing. I generate the random part, and then I add this function to all the samples. So the best thing, get rid of the mean. You know, when you deal with real data, I'm working right now on some project on climate change, and we have the data, and we have to do something about that, to clean them a little bit. You have the seasonal variation and all these things which come in two flavors, mean and variance. So we try to make them as stationary as possible. So this you try to estimate the means, yearly or seasonal means and variance, and then you scale the samples and hope to be sort of stationary. Okay, so these are the examples. These are just a few examples. There are many others. So as before, tau, it's the time lag. This should be, don't put new k here, put a new c. And I'll tell you right away G0 and new c is. Lambda, sigma, these are the symbols here. So these are the correlation function. And these are the spectral densities. First one, I give you just a picture. So you know right now what G0 nu CR. So 0 nu C is the frequency band. G0 is the intensity, is the spectral density. And of course, all of these things, they come with a name. This is called band limited white noise, and I think the name is obvious. White noise is a constant spectrum from 0 to infinity that has constant spectrum, so from 0 to this cutoff frequency nu C. So it's called band limited white noise. Spectral density for the second process. Well, lambda, I didn't say lambda, of course, it's something positive. This is so-called first order Markov process.
Sorry, in that formula, what is the u in the denominator?
This nu is this argument. Is an argument. Sorry for the typo. Yeah, it's the same argument. The spectral density is a function of the frequency, which is nu, right? So what the other. And the final and the name of this is second order Markov process. Of course, I didn't give you any definition what Markov is, but I can give you some intuition on it in a very simple setting. You may remember the first example I made here about random processes, maximum daily temperature in Liverpool. If the correlation function of that particular time series depends only on lag 1, that is 1 day lag correlation, that called Markov of first order. If it depends on the first 2 lags, it's Markov of the second order. And this is a continuous version of that process. Okay. Now, coming back to the discussion we had before, if this would be a white noise, a full white noise, that would extend all the way to infinity. And you remember what we discussed, that the variance of the process is the area under the spectrum. That is, would be this area under this infinite rectangle, therefore it's infinity. What's the variance of this process? Come on, you have to tell me right away. Area under the spectrum, what's the area of a rectangle? G0 nu c, right? Okay? All right. Let's try to generate a sample of one of these processes. It doesn't matter which one, it's all the same. So the method I'm going to describe it right now is so-called the spectral representation theorem, because it's based on the decomposition of the spectrum. So Monte Carlo simulation. Algorithm. The step 1 is to discretize the spectral density. I'm going to draw the spectral density and show the discretization. Let's say this is a spectral density. It's a general form. And we discretize it. That is, we have to take some intervals and take the midpoint of these intervals. So that would be frequency nu1, frequency nu2, so on, frequency nu k, so on. And depending on the form of the spectral density, if that spectral density is not like this, but extends to infinity, we have to select the cutoff frequency, right? So this is a cutoff frequency. Now, when you do this, you already made a big approximation, right? That is, you know that you are not going to consider that power of the process. Because you don't look, you are not going to model. Right? Everything is stuck here. Now, is this relevant or not? Is no general answer. It depends on the objective. For example, if this process is an input to a linear system, and let's say a single degree of freedom system, and the natural frequency, it's in this range. Probably it doesn't matter if the damping is not too high, because anyway, the system is not going to see frequency in this band. So it doesn't matter. But when we are going to do later on, to go from a Gaussian to a translation process, we have to adjust for this because otherwise the area is going to get screwed up. And I'm going to tell you what to do in that particular case. Okay? So let's call this the last frequency we keep. Here's nu n. Now, what typically is done is to divide the frequency band 0 to nu c in equal intervals and take this frequency at midpoint. You don't have to do that. I'm telling you what is frequently done, or most of the time done. So if frequency intervals are equal, and this frequency nu k are midpoints, as I discussed, then our representation would include harmonics of frequency nu 1, nu 2, nu k, nu n, right? This is going to be our representation. Then the signal is going to have a certain period. And what would be that period? So in this setting, this is a frequency interval, this is the same frequency interval, and so on, right? And nu 1 is half of this interval, nu 2, and so on. What would be the period? Well, yeah, that's right. It would be 1 over nu 1, right? So that, if you create a signal, which period, depending whether you go radian or hertz or whatever, with period longer than 2 pi divided by nu 1, you are going to repeat the signal. Okay, shall I say it again? Don't think probabilistically for the moment, right? If you have a Fourier representation, what is the first thing when you construct a Fourier series? You said that's my interval, right? And then you said the period of the interval is going to be this. If we start with this frequency, the period of the sample you generate would be 2 pi if you go in radian divided by nu 1. If you produce a sample longer than that interval, you are going to see the same sample over and over. Okay? So if you are in fatigue studies and you need a very long samples, that is a problem. How you can overcome? Well, the hard way or the smart way. What's the hard way? Decrease its frequency interval as much as possible. And then when you decrease the frequency, the period becomes longer and longer. But what that be the implication? You have a huge summation of frequencies. So that's not very good. There are smarter ways to do it. We don't have time to do it. If you're interested, I can give you a reference. The idea is to randomize the frequency in each interval, and that overcomes that thing, and you preserve all the properties. Okay? So that's a smart way. And there are all kinds of other techniques, sampling theorem and stuff like that, but let's focus just on this one. So let's say we're done with the first step. We discretize. Let me introduce one more notation here. If you look at the area here, let's call it sigma k square. Then note that sigma k square is simply the area of the spectral density over this interval, right? And if you can add another notation here, and that's the last one on this picture, I sub k. That is the length of this interval. Okay, so that's the area under the spectral density centered on the frequency nu k. So now we have everything to put the things together. So step 2, we are going to approximate the process, which has this spectral density, by the following process. So this is a target process. and I'm going to approximate. I'm going to put an n here to indicate that our approximation is based on n frequencies. And guess what? We already know the formula by heart now. So let's see why this formula works. So sigma k is defined. Nu k are defined. So A and B are as before, uncorrelated with mean zero and various one. I'm writing exactly the formula we play with quite a bit. So what's the mean of that thing? It's any different from what we wrote before? Just look back on your pages. What was the mean there? Anybody find it? Because I forgot it, really. You have to help me here. Did you find? Did anybody find it? Come on, what shall I write here? The big example we started with. It was the sum of sine and cosine, and we calculate the mean and correlation function. Thank you. I just remember I know you mentioned. And what about the correlation function? Yeah, of course it's on the same page. Exactly. Okay. So you remember that we wrote the formula for the connection between correlation and spectral density by Bochner theorem? That was something like this. Remember that? Okay. I'm trying to bring it in this form to convince you that this is what we need. So I'm going some very cheap tricks. I'm going to do nothing really spectacular. Split it into parts and use the fact that S is an even function, and that does it. 0, infinity. Is that okay if I don't write the whole thing? As what's written there? Plus, minus infinity to 0, and now I'm going to write the whole thing. So I just split the integral in two pieces, right? And then I'm going to do a change of variable here. That is, I'm going to send nu into minus nu. That would be the change of variable. And now you know what I'm doing, because it's obvious. It's a cheap trick, as I said. So if I do this, I'm going from plus infinity to 0, e to minus I nu tau, right? It's a change of variable. S of minus nu, which we know that it's even, that is true, is equal to 0. And minus d nu, right? And that minus is good because it makes me to flip the integral to in the right form. So then the whole integral becomes 0 to plus infinity So now I have to put the package together. So all this implies that, so I'm going to put the whole thing under the same integral, which has essentially has the same parts. Some are the same. The integrand is the same or not. One is exponential is plus, and the other is minus. So the first one is with plus. And you remember the identity? So when you add an exponential, I exponential with plus and minus, you get a cosine, double cosine. And now one more line and we have it. So it's cosine of nu tau 2 s nu d nu. And 2s nu, you remember we defined what the engineers like? They don't like the spectral density, they want like a one-sided spectral density. I'm on the positive frequency band. So this is exactly G of nu, one-sided spectral density. Can you read that low or not? Shall I write it in another place? So what you couldn't read? The very last one?
Yeah.
Okay, so the very last one, right in this parenthesis, 2s nu is G of nu. Could you write 2s nu or even that not? Okay, let me write it. Can you write it in this band? Okay. So is written integral 0 infinity cosine 2s nu d nu. And this 2s nu is G of nu. If you look one page or 2 pages earlier, you may note that this is G of nu, the one-sided spectral density. Maybe it's still defined somewhere. No, perhaps it's gone. Is that still defined? No, it's gone. It was defined somewhere here. If you cannot find it, I'll show you after the lecture. Okay? All right. So what do we have here? This is a correlation function of the model. And this is a correlation, I'm going to write it one more time, of a general process. Okay? Any relationship between them? Any relation? How you calculate this numerically? It's exactly that. Right? So, of course, you can prove formally that when the partition goes to 0, that is, the size of the partition goes to 0, this sum turns into a Riemann-Stieltjes integral, which is exactly that one. And the error depends, of course, of the discretization. All right. So now we showed this. The final step is to generate samples. Okay, so let's summarize one more time where we are. This is our objective, to produce an algorithm for generated samples of random processes, which are weakly stationary. First, we discretize the spectrum, and this is how we do it. And in the process, we have to select a cutoff frequency, so we are going to lose some variance. This is how we calculate this constant, which is using the representation, our model in step 2, and we show that the correlation of the model and the mean are simply numerical approximation of the target values. So we know that we are on the right track. What we have to do right now is to generate samples. So we are going to generate them in 2 settings, Gaussian and translation. Okay? So sample generation, A, Gauss process, So if the process is Gaussian, it means that A and B are not only uncorrelated 0, 1, are Gaussian 0, 1. And if they are uncorrelated, how else are they? I like to hear the choir, independent, right? In Gauss, uncorrelation independence is the same thing. So sample generation for Gaussian process generate independent samples of AK and BK, which are Gaussian 0, 1, and then calculate corresponding samples of X of t from the formula, right? A's and B's after we generate our numbers. We put the numbers in there and you're done. For translation, non-Gaussian processes, depending what processes you want, you have to choose a distribution, right? Let's suppose that F is a marginal distribution of the non-Gaussian process you generate. So translation non-Gaussian processes with marginal F. So let's call it differently because X is that thing. Call it Y, or okay, let's call it X sub T from translation. Okay? I'm going to put a tilde on the top of this X, and I tell you right away why. Xn. Okay, so I'm going to tell you. So it's a new notation, so big. Am I missing a parenthesis? I think I missed one, right? One more is to it. You see, in LaTeX will tell you don't have enough for MATLAB. Yeah. So I still own it to tell you what that Xn tilde is.
What about distribution where the CDF is not isolated, invertible?
Well, it's not a problem. You can invert anything numerically. So what we do in this setting, that happens quite frequently when you do with data. I mean, we don't have to, what we know is a catalog of distribution. World doesn't have to follow that thing. You either do it numerically, or in the data analysis, what we do, we simply fit some models, which may not be from the table. Yeah. And since they are monotonically increasing, you don't have problems. Where there are, you have to be a bit careful when you have jumps in the distribution. That is, you have atoms. Then you have to decide whether it's strict inequality or not. Yeah. All right. So I have to tell you this Xn tilde is. You know what Xn is. And you may remember I mentioned that we do something here which may not be exactly perfect. So what is the variance of Xn tilde? Is it 1 or not? Let's suppose that the initial, this process, the target process, X of t, has unit variance. What's the variance of Xn? It's 1, it's smaller than 1, or larger than 1. It's 3 options. So the probability of correct answer is 1/3. They are equally likely events. No, of course you are biased. You are going to be closer to the true answer. So what's happening? We're losing some variance, right, by cutting off. So the variance of Xn is smaller, always, than the variance of X. So this is a CDF of the standard normal. So when I apply the CDF, I have to make sure that the variance is 1. Otherwise, I'm going to get biased results. So let me give you the definition of xn tilde. Oh, here it is. So x and tilde. It's our xn of t. And I'm going to scale it by its own variance. So in this way, or standard deviation rather. Standard deviation is square root of variance. Right? So by doing so, of course, x and tilde has unit variance. And that formula makes sense. Because unless I have here 0, 1, when I calculate the output distribution, it's not going to be f. It's going to be something else. Okay? Okay. So we spent quite a bit of time on weakly stationary processes. And what was the essential constraint on these things? Constant mean and correlation function that depend just on the time lag. But this definition involves only the first 2 moments. Question, is it a stronger definition of stationarity than that? And the answer is yes. And this is a stronger definition of stationarity. So it's standard. When any time is called weak, refers to the first 2 moments. And because it's an expectation, it's a global property. Maybe some of you are involved in all kinds of finite element studies, and you have a strong and weak formulation. All the finite elements are in the weak formulation. Why? Because they can prove very easily convergence. In the strong formulation, convergence is virtually impossible unless you go to special cases. It's when you go deal with Gaussian processes, weak and strong is the same thing because the first 2 moments define completely the distribution. But when you deal with non-Gaussian processes, as I mentioned perhaps several times that in my opinion the world is not Gaussian, it's important to understand that concept. So, thank you again. xt. Some people refer to it strongly, stationary. I put it in parentheses because generally people just call it stationary and mean strongly stationary process. If for any n and any times t1 up to tn. So let's start before I continue. So I said I'm going to look at n time instance, t1, t2, tn. Both the number of these times I'm going to look at and their location, it's totally arbitrary. And one more, and time lag. We have the following thing. If you look at these vectors, so what I wrote on the board there, the value of the process at time t1, t2, tn. So this is an n-dimensional vector, right? And I'm going to consider another n-dimensional vector. these are, thank you. These are two-dimensional vectors, right? Two n-dimensional vectors. So again, n, the number of times I'm looking at, and precisely the times are completely arbitrary, as well as a lag tau I'm looking at. So I'm requiring that this vector is this vector have the same joint distribution. That if this for 5 equal to 5 these times, I'm looking at in this location or in this location or in this location, and I consider the vectors, this 5-dimensional vector in this case defined by these times. It doesn't matter where I'm looking. I'm going to see the same thing. So this is distribution, not first two moments, and all finite dimensional distributions. Okay? That's a much stronger properties. So the following statement holds. Strict stationarity. And I'm putting double S just to emphasize this. Do you think this is true? That is, the statement is strict stationarity implies weak stationarity. Just a guess. Well, if n is equal to 1, in that definition of strict stationarity, what does it mean? Then the distribution of x of t, regardless where I'm looking at the time axis, is the same. So what is going to be the mean? It's going to depend on location in time? No, so the mean is time invariant. So let's say if n is equal to 1, that implies that the distribution of x of t is equal to the distribution of x of t plus tau for any t and any tau. So how calculate the mean? This is a random variable right now, right? How you calculate the mean? Integral of x df, right? So that implies that the integral right? So it's the same at all times. If it's the same at all times, that means mean is constant. If n is equal to 2, it means that so x of t plus tau, or t rather, t and x of s has the same distribution as x of t plus tau and x of t plus and x of s plus tau. Right? How calculate the correlation? How we calculate the correlation of such a thing? Right? So the correlation is this: x of t, x of s, it's equal to double integral, right? Say x and y. X is t and s, right? T. That's a correlation, right? But this distribution is the same as the distribution of this. Let me write it clear because you may not be able to read anything. by strict stationarity. So what I calculate is a correlation function of this S and T, or S plus tau or T plus tau, it doesn't matter. So all it matters how far apart they are. So it's just a function of tau. So what did we show? That if the process is strictly stationary, the mean is constant, and the correlation function depends just on the time lag. Therefore, this holds. Guess what? The other way is not going to work unless what? Guess. Come on, guess. What's such a special thing in the world that everything works, unless Gaussian, right? So weakly stationary Gaussian are also strictly stationary. And there are some other examples, but this is the most dominant example. And I have much more stuff here to do, but it's 3 o'clock, so I don't know if I should start something else or not.
So you can also
Go into, yes,
do something in the last session,
yeah,
which is left over, and then
that's right.
do it. That's fine.
Okay, so I think we stop here, and I guess you already had enough of me today, but it's not over. I have bad news for you.
So there's a half hour break now, coffee.